Hi everyone. So this video is going to be talking about the increasing and decreasing intervals for both the shot put problem as well as a generic quadratic. And so the whole concept of the increasing and decreasing intervals, it all comes down to the fact that parabolas are indeed symmetric. And that vertex, actually, let me figure out what that exact value is first. 34.176. Okay, 34.176. That vertex value is the turning point, of course, of the parabola. By definition, vertex is the turning point. And so for that same reason, the vertex also divides the parabola, if you will, into its two symmetric halves. And which side is which? Well, it kind of just depends on if the parabola is right side up or upside down. But on this particular parabola, you can see that it is the left side that is increasing. So all of these dots are increasing, 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 increasing until you hit the vertex, of course. And then everything on this side, the right-hand side, is decreasing. And so essentially, when we divide the parabola into the left and right halves, we are acknowledging the two intervals. So let me see if I can draw on my Desmos. I think I can, but I'm not positive. So yes, I can. So the left half of this parabola is increasing. And for this parabola, it's the right half that is decreasing. So the fact that you divide the parabola into left-right halves really helps illuminate why. When you draw the intervals for this mathematically, like lay them out notationally, you are referring to the x values. This parabola is increasing from its starting point all the way up until it hits that turning point. This little range of values right here from there, from 0 to the vertex, that's the quote left side of the axis of symmetry. You're not making reference to the y values. The y values get reused. If you think about it, the y values on this parabola are all repeated. On the left-hand side, it starts at 6 and it goes 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, all the way to the 23. And then on the right side, it starts at 23 and goes 22, 21, 19, 18, 17, 16, 17, 18, 19, 5, 4, 3, 2, 1. But you reuse them all. Every single output on the left reoccurs on the right. That's not unique. They're like just duplicates. It's the x values that differentiate one side from the other. So for this one, the left side goes from 0 all the way up to, again, the vertex at 34.176. But then notationally, how do we say between 0 and 34? Well, it's inequality notation. The same way that we do our practical domain and range, it's inequalities. So notationally, what I have written right there is that it increases starting at 0 all the way up through the d values until you reach the vertex at 34. And notice there's no equal to bar on the 34. We'll come back to that. And then for the right half, well, the right half picks up where the other one left off, so at 34, and then it continues all the way until you hit the x-intercept. For this particular problem, you'll stop at the x-intercept because once the shot put lands on the ground, we no longer care about keeping track of it. So this interval starts at 34 and ends at the horizontal intercept, which is 73.9. So then notationally, everything above that, all the way up to 73.9. Now, again, notice my intentional not inclusion, no equal to bar, on the 34.176. And that's because the vertex is indeed the dividing line between the two halves. Yes, it is the dividing line. But at that exact moment, at 34.176, it is neither increasing nor decreasing. You're done traveling uphill, and then you hit that peak. You're in limbo for just a second. And then you start traveling downhill. But at that exact location of vertex, you are neither increasing nor decreasing. And that is why we do not include the equal to bar on that number. So your intervals are always inequalities, always, always, always inequalities. And for this particular shot put problem, those are the two inequalities. Now the other one, if you're not done with the shot put problem, pause this video, go finish the shot put problem. But when you're ready, you'll move on to the back side of the document. And on the back side of the document, the formula is different. Oops, I need to clear all my markings. There we go. The formula is different. It's y equals 2x squared plus 8x minus 7. And the vertex on this one is at -2, -15. There we go. So right there is the vertex. And on this particular graph, let me purposefully change my x-axis so that I can see, whoops, I didn't mean to do that. There we go. Change my x-axis so I can see it a little bit better. So let's just go like -7 up to like 3. And then my y values need to go down though, because the vertex is at -15. So how about like negative, I don't know, 20. Okay, there we go. I like that window better. So for this one, which interval is which, right? Which side is increasing versus which side is decreasing. You just have to be careful because on this particular graph, the left side is the one, whoops, the left side is the one that's going downhill. And it's the right side, or the right half, that's going uphill, increasing. So you just have to be careful, you know, there's no, it always does this on these ones. Every parabola is different, right side up, upside down. And for that reason, you just have to think carefully about which is which. Now for this one, the left side is everything to the left of -2. That's where the axis of symmetry or the vertex is on this one, is at -2. So everything to the left of -2 is the decreasing side. And then similarly, everything to the right of -2 is increasing. Now, there is no stopping point on this one. If you recall, the domain for this one is simply all real numbers. It is not a word problem. It does not stop ever. It goes on forever. So as far as the left side, all you need on this one is a singular inequality statement. The only reason we use compound is to have a starting point and a stopping point, like on the shot put problem. It starts here and it ends there. But on this one, there is no stopping point. So the notation is shorter for that reason. So how do you say everything to the left of -2? Well, all the values to the left of -2 are technically less than -2. Think about that, right? Everything to the left of -2, you know, like -3, -4, -5, -6, -7, those are all to the left of -2. Those are all less than -2. And then similarly, on the right-hand side, everything to the right of -2. Well, if you're to the right of -2, then what you're referring to are x values again that are technically bigger than -2. Think about that, to the right of -2. So, you know, like -1, 0, 1, 2, 3, 4, 5. Those are all the numbers to the right of -2. And so technically that is greater than -2. Once again, notice no equal to bars, right? Because at that exact moment, at -2, it is neither increasing nor decreasing. It's that bizarre point of limbo. Everything prior to that, decreasing. Everything after that, increasing. But at that moment, neither. So we purposefully leave off the equal to bars for that reason. So my recommendation on these, to be totally honest, is to start with the English words. Start by just acknowledging which half are you talking about? Which half is decreasing? Well, the left side, the left half. Start there. Because if you start there, then you can start to pay attention to what values you need. If it's a word problem that starts and stops, well, then where does it start and stop? On the left side. If it's not a word problem, well, then you only need one statement, but still, to the left of what? Where's your cutoff? For this one, the cutoff was at -2. Everything to the left of -2. That's what your notation has to say. So again, start with the English words, right half, but then ask yourself, okay, to the right of what? In this case, it's to the right of -2. So your notation has to say, mathematically, of course, everything to the right of -2. So hopefully that helps with your intervals. Obviously, if you have questions, you know where to find me, but my hope is that it helps. And yeah, let me know if you have any questions. Thank you so much, guys.